Hello! A pleasant day to all of you. We are the Group 2, and we will be performing the lab exercise number 4, or the switches and 7-segment display. So what are we waiting for? Let's start! So for the problem number 1, we are asked to write a C++ program for the Arduino Uno as described below. So we are making sure to include an initial block of comments at the start of each program and as well comments throughout. We're gonna compile each program using the Arduino IDE and correct any errors that occur. So for the following conditions, the count should be initialized to 0 as shown on the 7-segment display and the computer screen. When the user presses the button, the count should advance, and the new value should be displayed on the 7-segment display and the computer screen. Next, the count should be mod 10 or 0 to 9 and repeat. And we're gonna use the display digit function described presentation for this lab. And we're gonna use the read button function provided in the presentation for this lab to allow for switch debounce. So, as you can see here, for the red color on the code, so we're gonna supply this with the given conditions. So let's start by opening our Arduino IDE. So I have prepared the Arduino IDE already for the problem 1. So to start the program, we're gonna add a comment here, name pin definition. So we're gonna add constant int, we're gonna call it button pin, and if it will be equals to 9. It is assigned to number 9 since we're gonna connect it, or the pin connected to the button. Next, we're gonna call another button pin, or button pin assignment. We're gonna name it segment pin. Bracket. It will be equal to, inside the curly brace, 2, 3, 4, 5, 6, 7, and 8. These numbers will be assigned on the pin from pin number 2 to pin number 8. So pins assigned or pins connected to the 7-segment display. Next, for the global variables, we're gonna initialize or add a counter that will be equal to 0, since the counter will start at 0. Next, we're gonna add a boolean function, and last button state equals to low state. So this will be the previous state of the button. Next, for the void setup, gonna add the curly brace. We're gonna define the input and also the output pins. So pin mode, we're gonna call the button pin as shown in line 2, and make it input. Next, we're gonna add a for loop for int I is equals to 0 and I is less than 7, we're gonna add it, or I++. Next, curly brace and pin mode. Segment, gonna call the segment pins. And inside the piece the I, and make it an output. Okay. Next, we're gonna add or set up serial communication. We are always making sure that we add the serial begin with 9600 baud rate. Next, for the display instruction on the computer screen or the serial monitor, we're gonna add serial print line 7 segment display counter. Next, I'm just gonna copy this, paste, gonna change this and press the button to increment the counter. Next, another display the initial value which is 0 on the 7 segment display. Display underscore digit unit counter. Which is on the line number 6. Next, we're gonna add display the initial value 0 on the serial monitor or computer screen. Gonna add serial print, name it count. Next, serial print line, name it, and this is where the counter or the count will display on the line of 28. We're gonna call the line number 6. Okay. Next, for the void loop, braces, we're gonna adjust the counter for mod 10 operation as stated in the problem. Gonna add if statement, if counter is greater than or equal to 10, add the curly brace, then counter equals to 0. Next, display count on the computer screen also. Serial print, count, serial print line, name it counter. Next, gonna also display count on the seven segment display. And I'm just gonna copy the line 24 because it also have the same code as here in the void, inside the void loop. Okay, we're now done. Next, we're gonna call the boolean read button int button pin. This will record the number of times the user clicks or toggle the button. We're gonna call another bool inside current button state will be equal to the digital read button pin, which is on the line number 2. Next, if statement. If the current button state equal to the high and the last button state is equals to low, and we're gonna add the bracket or braces. Delay, we're gonna add a delay of value of 50 milliseconds. This will serve as a debounce delay. And inside of it, also another if statement. If digital read or inside the button pin is equals to high, last button state is equals to high. We're gonna return it, return true. Okay, next, gonna add another if statement here, new if statement. If the current button state is equals to low, and then we're gonna last button state will be equal to also low. We're gonna return false. Next, we're gonna add void a new display digit. Int n curly brace. We're gonna define the segments for each digit. For each digit from 0 to 9. The constant byte digit 10, since we are gonna add the segments from 0 to 9, and 7 equals to braces. Under it will be the curly brace, high, 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 low. This is for the number 0. Next, I'm just gonna write it down. Number 1. Next, for number 2, high, 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 low, high, high, low, high. For the third one, high, 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 low, low, high. Next, for the fourth one, low, high, high, low, low, high, high. Number 4. Next, for the fifth one, high, low, high, high, low, high, high. Number 5. Next, we're almost done. Number 6. For the sixth one, high, high, low, high, high, number 6. For the seventh one, high, 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 low, 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 low. Next, for the eighth one, high, for 8. For the last one, high, 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 low, high, high. Next, under it, we're gonna add a for loop for int integer I is equals to 0 and I is equals to less than 7. We're gonna add it, or I++. Inside of it, we're gonna add the digital write, segment pin, I, digit, N, and also the I. For the line 73 to 74, its purpose is to set the segments according to the digit being described on the display. Set the segment according to the digit. So that's it for program 1. So I'm gonna pass this for output checking to Daniela. So take it away.
Hello everyone, so welcome back to another Arduino demonstration. It's me, Danny, and we are now at our 4th laboratory exercise. So we are heading on over to switches and 7-segment displays. So to begin with the lab exercise, let us see the problem number 1. So just having a bit of a problem. So I have my Tinkercad simulation right here, and we can now head on over to my board. So my board is pre-built because I have recorded this scene, this introduction in problem 1 for about a lot of times now. So since I've got the right build for the 7 segment, I decided to not redo it again. So as you can see, I have here my lit up 7-segment display, and what this circuitry would do is would display numbers from 0 to 9. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. So that's it for problem number 1.
Hello everyone, today I will be walking you through the implementation of 2 types of up or down counters using an Arduino Uno board. The first counter uses a toggle switch to control the counting direction, and the second counter allows the user to preset a starting number using dip switches and interactively control the counting direction with a toggle switch. Now let's start coding our problem number 2. Let's start by defining the pins that will be used for the 7-segment display and the toggle switch. Pins 2 to 8 are assigned to the segments of the 7-segment display, and pin 9 is assigned to the toggle switch. So let's type const in seg A equals to 2 and semicolon. Next, const in seg B equals to 3. And next is const in seg C is equal to 4 semicolon, and const in seg D equals to 5 semicolon, and next const in seg E equals to 6 Next is const int seg f is equal to 7. Next is, let's type const int seg g is equal to 8, semicolon. And last is const int slide switch pin equals to 9 for the pin for the toggle switch. Next, we define the binary patterns for each digit 0 to 9 in an array. This pattern controls which segments of the 7-segment display are turned on to represent each digit. So, let's type const byte digit patterns. Then, bracket. Inside that bracket is number 10 equals braces. And then, first for 0 is 0B, 0, 0, 1, 1, 1, 1, 1, 1. And next is 0B, 0, 0, 0, 0, 0, 1, 1, 0. That's for 1. Then for 2, 0B, 0, 1, 0, 1, 1, 0, 1, 1. Next, that's for 2. And for number 3, 0B, 0, 1, 0, 0, 1, 1, 1, 1. That's for number 3. Then for number 4, 0B, 0, 1, 1, 0, 0, 1, 1, 0. Next, for number 5, 0B, 0, 1, 1, 0, 1, 1, 0, 1. That's for number 5. And for number 6, 0B, 0, 1, 1, 1, 1, 1, 0, 1. For 7, 0B, 0, 0, 0, 0, 0, 1, 1, 1. Then for number 8, 0B, 0, 1, 1, 1, 1, 1, 1, 1. And for number 9, 0B, 0, 1, 1, 0, 1, 1, 1, 1. That's for switch 9. Then for counter variable, let's type in counter equals to 0. Don't forget the semicolon. Then in the setup function, we will initialize the segment pins at outputs and the toggle switch pin as an input. We then call the display digit function to display the initial counter value on the 7-segment display. So let's type for open and close parenthesis. Inside this int I is equal to seg A semicolon I less than or equal seg G semicolon I plus plus open and close parenthesis. Next is braces. And then in mode, open and close parenthesis. Inside that is I, comma, and then output. Next is pin mode, open and close parenthesis. Inside that is slide switch pin, comma, input. Then next, display digit counter. The counter is inside the open and close parenthesis. This is to initialize display with initial counter value. Then in the loop function, we will read the state of the toggle switch to determine the counting direction. If the switch is on, the counter increments. If it's off, the counter decrements. We use the modulo operator to ensure the counter wraps around correctly 0 to 9 or 9 to 0. After updating the counters, we will call the display digit function to update the display and the delay for 0.75 seconds. So for void loop, let's type bool up direction is equal to digital read slide switch pin inside the open and close parenthesis. And next, to update the counter based on switch state, let's type if open and close parenthesis up direction and the braces counter is equal to open and close parenthesis counter plus 1. And outside that is a character which is percentage. Then 10. To count up and else statement braces counter is equal to open and close parenthesis and inside that is counter plus 9. And outside that is percentage and then 10. That line of code is for countdown. And next, to display the current count, let's type display digit open and close parenthesis. Inside that is counter. Then semicolon. And next, for 0.75 seconds delay, let's type delay open and close parenthesis 750 and then semicolon. And then last, for the display digit function, takes the digit 0 to 9 as input and sets the appropriate segments on the 7-segment display based on the binary pattern for that digit. So to display the function on the 7-segment display, let's type void display digit open and close parenthesis int digit and then braces outside the open and close parenthesis and byte pattern is equal to digit pattern and then bracket digit and semicolon. Next is digital write open and close parenthesis We will start on seg A, comma, pattern, and the array 0B 0 0 0 0 0 0 0 1. And semicolon. Next is digital write or seg B. Comma, pattern, and 0B 0 0 0 0 0 1 0. Then next, digital write or seg C, comma, pattern, and 0B 0 0 0 0 0 1 0 0. And digital write or seg D, pattern, and 0B 0 0 0 0 1 0 0 0. The seg column. Next is digital write or seg D, pattern, and 0B 0 0 0 1 0 0 0 0. Next, digital write or seg pattern, and 0B 0 1 0 0 0 0 0. Last is for digital write, seg C, seg G rather, and pattern, and 0B 0 1 0 0 0 0 0 0. Don't forget to put semicolon. That's the code for program number 2.
Okay, so moving on to problem number 2, we have the circuitry right here. So let me just do it on my board. Real quick, I'm recording this. Okay, so let me see. So this is here. Let me move my resistor to the middle part. Is this still on the negative? Yep. So middle part, and then this is on the. Is this on the 9th still? Yes. Okay, so I still have the same arrangement. So I just changed my switch. I changed it into a slide switch. So let me connect my board. Oh, okay, and then run my code right here. Did I? Oh, I didn't. Let me choose the port for this one. and the board. Upload the code. Okay. Oh, what should this be doing? Oh, I think it's doing it on this. Am I doing it right? Oops. Okay, so I got it right. So I just made some mistake. So when I slide my switch to the left one, it displays number decreasing. It displays decreasing numbers. And when I slide it to the right side, the number increases. See? So that's it for problem number 2.
In the third problem, we will implement a counter where the user can preset a starting number using a 3-switch dip switch. The counting direction is controlled by the toggle switch. The counter can be switched from up down interactively with each count interval delayed by 0.75 seconds. So first, we will define pins. For the dip switches, pin 10 to 12, the toggle switch pin 9, and the 7-segment display segments pin 2 to 8. So let's type const int dip switch pins then a bracket. Inside it is 3. Equals to open and braces. Inside that is pin 10, 11, and 12 for the dip switch pins. And for the toggle switch pin, let's type const int toggle switch pin equals to 9. And for the 7-segment display pins, let's type const int segment pins and a bracket. Inside that bracket is pin number 7 equals to braces. Inside that is pin 2 to 8. 2, 3, 4, 5, 6, 7, and 8 for the 7-segment display pins. So let's correct the error in line 2, which is the missing const int toggle switch pin 9. There you go. Then next, Let's type in pin underscore 2 equals to 12. Put the semicolon. The next is in pin three or 11, and last is in pin 4 is equal to 10. And in current count is equal to 0. And then bool count up is equal to true. So we define the binary patterns for each digit, which is 0 to 9 in an array. These patterns control which fragments of the 7-segment display are turned on to represent each digit. So let's type const byte digit to segment bracket inside this number 10 is equal to braces. Binary numbers for G 0, B 00 11 1111. Next is B 00000110. For number 2, B 0101011. Then for number 3, B 01001111. And for number 4, B 01100110. For number 5, B 0110 1101. So let's correct our mistake here. Let's change the semicolon to comma. So for number 5, B0 110 1101. Number 6, B0 1111 101. For number 7, B0 0000 111. For number 8, B0 111 1111. For number 9, B01 10 1111. So in the setup function, we initialize the dip switch pins as inputs with pull-up resistor and the toggle switch pin as an input with a pull-up resistor. We then read the initial values from the dip switches to set the starting count. The display number function is called to display this initial count on the 7-segment display. So let's type serial.begin 9600. So this line is to start the serial communication. And next, we will set dip switch pins as input. First is pin mode, pin underscore 2, and then input semicolon. And next is pin mode, pin 3 underscore 3, and input. And next is pin mode, pin 4 underscore 4, and then input. And next, to read the initial dip switch values to set the initial counter value, let's type int val underscore bit 4 is equal to digital read pin 2. Then next is int val bit 2 is equal to digital read pin 3. Next is int val bit 1 and digital read pin 4. And we will convert the binary deep switch values to a decimal value. So let's type in des val is equal to open and close parentheses 4 times val underscore bit 4 plus open and close parentheses 2 times val underscore bit 2 plus open and close parentheses 1 times val underscore bit 1 and then next don't forget the semicolon. Next is current count is equal to decimal over val. That will set the initial count based on deep switch input. So next, we will set deep switch pins to input with internal pull-up resistors. So for open and close parentheses, int I is equal to 0, semicolon, I is less than 3, semicolon, and then I plus plus, then braces, and then pin mode, open and close parentheses, deep switch pins, and bracket I, and input, and then underscore pull up. Then to set the toggle switch pin to input with internal pull up resistor, let's type pin mode, open and close parentheses, toggle switch pin, and then input underscore pull up. And don't forget the semicolon. And to set the 7-segment display pins out as outputs, let's type for open and close parentheses int I is equal to 0, then semicolon I is less than 7, semicolon I plus plus, and then recess, pin mode, open and close parenthesis, segment pins, and then I. Next is output. Then semicolon. Next, to display the initial counter value of the 7-segment display, let's type display number, and then current count, open and close parentheses inside it, and then a semicolon. In the loop function, we read the state of the toggle switch to determine the counting direction. If the switch is on, the counter increments. If it is off, the counter decrements. We use the modulo operator to ensure the counter wraps around correctly 0 to 9 or 9 to 0. After updating the counter, we call the display number function to update the display and the delay for 0.75 seconds. So to read the toggle switch state to determine counting direction, let's type if digital read toggle switch pin is equal to low, and then count up is equal to true. Count up if toggle switch is low, and then else statement. Braces, and let's type count up is equal to false, count down if toggle switch is high. Then for the delay, open and close parenthesis, $750 is 0.75 second delay between counts. And next, to update the counter based on the counting direction, let's type if open and close parenthesis count up, and then braces, current count plus plus, and then a semicolon. Next, if current count is greater than 9, and the braces, then current count is equal to 0. It will wrap around to 0 if counter exceeds 9. Then an else statement. Current count dash semicolon, and then if current count is less than 0, then current count is equal to 9. This is to wrap around to 9 if counter goes below 0. To display the updated counter value of the 7-segment display, let's type display number, current count, and put a semicolon, and for the function to read the current value from the dip switches, let's type int read dip switch, open and close parenthesis, and then erase. Next is int value is equal to 0, and then for int I is equal to 0, I is less than 3, then I plus plus. Then the braces. Next is if open and close parenthesis digital read, and then inside an open close parenthesis is another open close parenthesis. Type deep switch pins bracket, inside it is an I, and then outside the first open and close parenthesis is a double equals, and then type low. Outside it is a braces, then value absolute equals open and close parenthesis 1 less than I. This is to set the corresponding bit if the switch is low. Next, to return the combined value of the deep switches, let's type return value. Last, to display the number function, takes a digit 0 to 9 as input and set the appropriate segments of the 7-segment display based on the binary pattern for that digit. First, for function to display a number on the 7-segment display, type void display number int num, and then braces, byte segments is equal to digit to segment bracket, num, and then the next is for int I is equal to 0, and then I is less than 7, and I plus plus, and the braces. The next, digital write, open and close parenthesis, segment pins, bracket inside it is an I, and then segments, and open and close parenthesis 1, and less than I. This is to set each segment based on the pattern. Then last is serial.print ln. And next is open and close parenthesis segment pins, inside the bracket is I, and then don't forget a semicolon. That is to print the segment pin number for debugging. So this is the code for program number 3.
Okay, so moving on to problem number 3, I have my circuitry here. So as you can see, they've added a dip switch. So I have my dip switch right here. So let me just put it over here, and then let's fix the wirings for this one. So, I seem to have a problem. So let me just, I think I can remove this, right? Oh no, I have to, where is this one? So this is 3 volt. Oh, this is ground, and let me just put it here so that I can put more cables. Okay, I need 3 more resistors. Okay, I can have 1 more. So to put this on the port connected to the negative, this one here, one here. Okay. So one more. We're here. Then one last for this one. Wait a second. Switch. Okay, so that's that, and then let's connect the fourth. What is and then tenth? Something over here. Green. For the third. Put the side. Oh, this one is broken. New cable. And here. And I need just one more. Oops, one more cable. Okay, for the second. The side is 13. 12. 12. Okay, so let me see if this one should work. Problem 3. Okay, so let me connect my board first. And select board and port. 12, and then uno. Let's upload. Yep. Now it's uploaded, so I think okay, so the dip switch serves as our binary numbers 1 to 4. So and then just this slide switch is just the same as our problem number 2, where when we slide it on the right side, it counts up it increases the counting, and then when it slides to the left side, it decreases. So I think we can first set our switch to this is let me try if it starts. Okay, so since I've set my dip switch to a number 3, you can see that when I start the uno, let me just okay, let me try this again. Oh, I forgot the cables above the switch. I'm so sorry. That's why it wasn't working. And then one more. It should be connected to the let me try if number 3 works. This is 3. It's 1 and 2. There you go. So since I've said that this is a binary counter and the slide is switched to the left side, when we open the binary, it starts with number 3 and the number is decreasing. So let me start off with another number. So let me add this one. So this should be number 7. It should start with number 7. When we open this, there you have it, number 7 on our display. So let me just slide this switch on to the right side, and then let's see, we have number 7 and the number is increasing. So that's it for problem number 3, and we have it.
Hello everyone, good day. I am Fritz Cedric Villarisa. For program number 4, traffic light circuit with 7 segment down counter, I will be demonstrating to you on how to manually type this code in Arduino IDE. So I'll teach you the step-by-step tutorial on how to comply this one. So first, let's define the explanation regarding this program number 4. So connect 3 LEDs, green, yellow, and red, and 3 220 ohm resistor to the digital output pins of our choice. Second is write a program to simulate a traffic light where the green LED is on for 9 seconds, yellow if on for 1 second, and red is on for 8 seconds. Provide synchronized timing to the down counter. The traffic light should operate forever. Run the program and verify that it works properly. Demonstrate proper operation of the program to the instructor. So first, we need to have this 3 LED colors. So green, yellow, and red for our traffic light. And second, we need to write a program that will simulate the green LED, the yellow LED, and the red LED. So basically, in the 7 segment timer, the countdown will start at 9 seconds and it will count down to 8, 7, 6, 5, 4, 3, 2. When the 7 segment triggers the digit 1, it will toggle the LED to yellow, and therefore the green LED will change its state to low. And when it makes 0 or the timer repeats, it will therefore toggle the red, and the yellow status will be also in low state. So that's what we have to do in this Arduino IDE. So first, let's zoom in a little. Let's first define our LED pins. First, we need to have constant green LED 11, constant in yellow LED equals 10, and constant in red LED equals 9. So for this program, we use the 7 segment common anode. Take note of the common anode. The middle pin is connected to ground. It opposes the common cathode because the common anode needs a resistor to each pins connected to A, B, C, D, E, F, G, whereas the common cathode doesn't need a resistor. It only needs a jumper wire to each pin, and the common cathode usually is connected to it's connected to positive, or the common cathode is connected to negative. Next is define 7 segment display pins. The constant in seg A equals 2, constant in seg B equals 3. Let me write this down. C, D, E, F, G. These are the 7 segment display pins. So 3, 8, 7, 6, 5, 4. So the explanation for this one is to have a definitions and initial setup for our program. So the purpose of this constant n is to define the constants for the pin numbers to which the LEDs will be go through, and the segments of the 7 display to the Arduino Uno. And I used this constant n because what do you call this? These pin numbers do not change even if there's an alteration of the code. You need to manually change this digital numbers in this code to define its place. So the importance of this code is to have a description for variable names and pin assignments that enhances readability and makes it easier to understand and modify the wiring or code. So when we need to define the hardware, we need to really have the guide for the software. So next, we will have this function to display a number on the 7-segment display with void display number. Display number is our variable with an argument of int number. Int represents positive numbers, switch positive whole numbers, I mean. Then case 0, we need to have the digital write, seg A low state. Then we have this digital write, seg B. So basically we will have this code now in our function. Digital write, seg C low, digital write, seg D low. So it's manually coded. It takes a lot of time to configure this. Seg E low, digital write, digital write, seg F low, and digital write seg G high. So the segment G is our pin on the 7 segment. Then break, you'd have this break section. So basically that's it for our case 0. So next is our case 1. We need to this code. We need to repeat this and have segment A high, low, low, segment D high, segment E high, segment F high as well, and segment G high as well. So the only thing in this case 1 is low is the segment B and the segment C. So that's it for our case 1. We need to really reiterate this code for our next cases. So case 2, same process but with different LED status. Segment A is low, segment B is low as well, segment C is high, segment D is low, segment E is low, segment F is high, and segment G is low. That's it. Next case, for our case 3, the digital write for this one, segment A low, segment B low, segment C low as well, segment D low, segment E high, segment F high as well, and segment G is high as well. Sorry, it's low pala. For our case 4, let's reiterate this code. Oh, sorry. Segment A is high, segment B is low, segment C is low, segment D is high, segment E is high as well, and segment F is low. Segment G is low as well. So that's it for our case 4. For the case 5, this is the syntax for our code, huh? Let's write this one. Segment A is low. Segment A is low, segment B is high. Segment C is low. Segment D is low as well. Segment E is low. Segment F is low. Wait, let me repeat. Segment A is low. Segment B is high. Segment C is low. Segment D is low as well. Segment E is high. Segment F is low. Segment G for the last part is low as well. So for our case 6, let me repeat this one. Segment A is low. Segment B is high. Segment C is low. Segment D is low as well. Segment E is low. Segment F is low. And segment G is low. For our case 7, let me repeat this code. Segment A is low. Segment A is low. Segment B is low. Segment C is low. Segment D is low. Segment E is... Segment A is low. Segment B is low. Segment C is low. Segment D is high. Segment E is low. High pala. Segment E high. Segment F is high. Segment G is high. So for a case 8, for our case 8, segment A is low, segment B is low, segment C is low, segment D is low, segment E is low, segment F is low, segment G is low as well. So basically, all of this case 8 states are on the low state. So case 9, segment A is low, segment B is low, segment C is low, segment D is low, segment E is high, segment F is low, and segment G is low. Now, we need to have this default status. So basically, let's write this and write the code for default. Segment A is high. All of these segments are high. So that's our code for void display number. So let me explain this segment very briefly. So this void setup, the purpose of this code block 18 to 43 is to have the set pin models for the LEDs and the 7 segment display segments as outputs, because they need to send out the signal to light up LEDs or segments into the Arduino Uno code. The importance for this one is to ensure that each pin is configured for output, which is crucial for controlling external components like LEDs and displays. So that's it. Let me explain this argument. This display number function, the purpose of this is to control which segments are turned on or off to display a specific number from 0 to 9 on the 7-segment display. Each case within the switch statement corresponds to a different number, controlling each segment state high or low. The importance of this is to modularize the code, allowing the display logic to be reused wherever a number needs to be shown on the display. Using a function avoids repetitive code and makes maintenance easier. So that's my explanation on why do I have to have this function. Next is to have this void setup. Void setup. Let me zoom in this one. Void setup. Comment initialize the LED pins as outputs. Pin mode. Sorry, pin mode. Pin mode. Green LED output. Yellow LED and red LED. Next is to initialize the 7 segment display pins as outputs. Pin mode seg A output. Then let's repeat this segment until segment G. Segment A, B, C, D, E, F, G. A, B, C, D, E, F, G. So that's what we need right now. That's our curly braces. Next is the void loop. The void loop and the void setup is to have the 7 display outputs and to send out the signal for the pin modes. The void loop, I'll write this code now. Let's have the comment green LED on for 8 seconds, yellow LED on for the 9th second. Digital write green LED high. Digital write yellow LED low. Digital write red LED low. For loop in I equals 9, I is greater than 1, and I less than display number I and delay of 1000 bits, 1 second delay for countdown. So that's it for our void loop. So the purpose of this void loop is to implement the logic for the traffic light sequence. It also controls the state of each LED corresponding to the traffic light color and uses a countdown to represent the time left before the light changes. The loop function is where the operational logic of the traffic light and the display counter is implemented using the previously defined function display number and the direct control of the LEDs via digital write. So that's the code. Next, for the yellow LED on for 1 second. Let's write this code really quick. That's how we do it. Yellow LED on for 1 second. Digital green low, digital yellow high, red LED low. For and I low, high, low, display number 1. Display number 1. Delay 1000 bits. 1 second delay. Display number 0. Delay of 1000. Green low, low, high number 1. Delay 1000. 1 second delay. Display number. Okay. Display 0 for the last moment. And finally, for another countdown, 8 seconds, but with red LED turned on, digital write. Let's write this one. Digital write. Where's the... The red LED has to have a high, low, and low. 8 seconds. Low, low, high for int. Wait, for int I equals 8. I is greater than 0. Then I minus minus. Display number I. Delay of 1000 bits. 1 second delay for countdown. Then we have to have this display number 0 and delay 1000. Display 0 for the last second. So that's it for our void loop. If you're wondering if I write this delay 1000 is to pause the program for 1000 milliseconds or 1 second between changes in the displayed number on LED state. This causes the sequence to have a delay like 5, 4, 3 like that. It defines the countdown timer. You need to tweak the 1 second delay for that, because if the delay is, for example, 200, so 200 milliseconds or 0.2 seconds, so the countdown will be 5, 4, 3, 2, 1. That's the explanation for the delay. And the traffic light countdown logic is to have the green LED being active for 8 seconds, counting down from 9 to 2. Each number is displayed for 1 second, because we will have a single 7-segment display, and the yellow LED phase will be turned on when it is turned to 1 second na. So the red LED phase is the another countdown for toggling the green and yellow and red. So basically the green is like the major countdown, while the yellow states that the ready countdown and the red is the another countdown. Follows with the red LED being on for 8 seconds, counting down from 8 to 1 and vice versa. So that's the explanation for code. Let's give it to test output for Daniela Francine Velasquez for testing out my code in this Arduino. So thank you for listening, Daniela.
With problem number 4, we need to add 3 LEDs. Okay, so our dip switch and our slide switch are no longer needed for this one, so let me just remove it. Okay, and then let me take this. Oh no, I can still use this 3, so I'm just gonna take 3 resistors here, because I'm gonna use it over here. Take this one, and I don't think I'm still gonna use a 3 volt. I don't think I'm gonna use a 3 volt, but I'm gonna use this one. Okay, so I have my yellow, red, and green LEDs here. Okay, so connecting this 3 resistors. I hope I don't forget to connect these. Sorry, one more. After this, okay, so 3. I have to start with number 9. Is this 9? So I have... This is 9, right? 9. And then that... Oops, sorry. So that... Okay. And then I don't think there's anything connected to the 12th pin. Okay. Should we start? I think we should. Okay. So let me connect my board. Oh, we have bullets. Let me change my yellow to another. Okay, so let me try running. So as you can see, I've already played the simulation. So as you can see, when the timer ends, it switches to another LED. So this is problem 4. Let me see if we can display our circuit. We can upload it. Upload. There you go. So as you can see, it's working properly. When the number is from 9 to 0, 9 to 0 ends, it switches to another LED color. Here we go. I can say that our problem number 4 is working properly. Let me stop this.
The idea we have is we'll use a slide switch to dictate what set of numbers will be displayed on our 7-segment display. When the switch is on, or in the high state, the display will cycle through even numbers from 0 to 8. Conversely, when the switch is off, or is in the low state, the display will show odd numbers from 1 to 9. Take note that when switching from one state to another, the program will finish its current set of numbers before proceeding to the next. Meaning, you can switch states in the middle of the sequence to change it from where it stopped. It will only change upon reaching the end of its sequence. Now, let's put that into code. First, we will declare the segment pins. Keep in mind whether your 7-segment is a common anode or a common cathode. Next, we will declare the switch pins where our switch is connected to the Arduino board. We also have a set of LEDs to represent the numbers that are shown on the 7-segment display. Let's also declare LED pins for our LEDs. Finally, let's declare the byte digits or the display digit patterns for numbers 0 to 9. And now for our setup function. First off, we have to set all segment pins that we declared earlier as outputs. To do this efficiently, let's use a for loop. After that, let's set switch pin as an input to identify whether it's on or off. Then next, let's set LED pins as output. Likewise with the segment pins, let's use a for loop. It's time for the main function. To execute our code flawlessly, we have to obtain the input from the switch. We'll do this by implementing switch state as a boolean that holds the state of the slide switch. Next, we'll determine the start and end numbers based on the switch state. Let's use a ternary operator, which is the question mark, to decide the starting value for the for loop. If switch state is true, the switch is high, so start is set to 0. If switch state is false, the switch is low, so start is set to 1. Then, let's set end to 10. We want to iterate through numbers up to 9, hence the loop will stop before reaching 10. Now, let's make a for loop to iterate from the start value to the end, incrementing by 2 in each iteration. So it's I plus equals 2. This increment by 2 ensures that we are only considering either even or odd numbers based on the start value. So if the switch is high or start is 0, the loop will iterate over 0, 2, 4, 6, and 8. Likewise, when the switch is low or start is 1, the loop will cycle through 1, 3, 5, 7, and 9. Finally, let's make a function to display a digit on the 7-segment display and control the LEDs. Let's name it displayDigit with parameter digit. Let's take the byte segments to correspond to the given digit from the digits array. Each byte in the digits array represents the segments that need to be lit up to display a particular number on the 7-segment display. Let's write the for loop. This loop iterates each of the 7 segments on the display, which is A, B, C, D, E, F, and G, and uses bitwise operations to check if each segment pin should be on or off. This next for loop will turn off all LEDs, so let's do it like this. This turns off all the additional LEDs by setting each LED pin to low. Now, let's turn on LEDs based on their current digit. This loop turns on a number of LEDs equal to the value of the digit. For example, if digit is 2, the first 2 LEDs in the LED pins array will be turned on. Let's also make sure that we do not turn on more LEDs than are available, only up to a maximum of 9. And that will be all for the code. Finally, let's go check out the next part for the actual demo of our program in action.
Okay, so moving on to problem number 5. As you can see, we have a bit of a complicated circuitry here. So, the problem prior here used 3 LED lights. So here we will be using 9, I think. Is it 2, 4, 6? Yes, 9 LED. I think I have it prepared, but let us see if... Let me see if I have enough resistors. Okay, so let us now try to build our problem 5. So let me first put my lead here. This is 1, this is 2, this is 3. This one is odd. Let me see if I have another. Where did I put that one? See here. There you go. So let me switch my irregular sized lid for a normal one. So yellow, green. I hope it fits because I don't know if it doesn't. I think I'm missing a red lid. So I'll just take another here. And another yellow. I really hope it fits. I think we're gonna make some adjustments. This is 3/6. Let me just right here move it so that everybody can fit. Okay, so we'll be needing 9 resistors as well. There, so as you can see, I have already placed my 9 resistors connected to my LED lights. So we will be needing... Okay, so we will be connecting all of our LEDs to the negative part of the board. Yeah. This here. Another here. Here. More cables. We are needing more cables. These are all connected to the negative. Hold after third. It's here. One. Last three. Last two. And then more cables are needed. Okay, so what are my not connected? Okay, these are all connected. So my until up to my 13th pin, I have to connect. Oops, why is it not? Oh, it's broken. It's still broken. I think these are, yep. These are male to female. Whoops! I knocked my camera. This one is male to female as well. Is this 13? Yep, 13. The 13th pin is connected to the 4th. This is store of the 1, 2, 3, 4. This is kind of complicated. This is 13. 12 is connected to the next. Okay, and the next is this blue one. Last two. The green. Blue is 11. 11 is second. Eight, 9, 10 is four. 2, 3, 4. Oh, I still have my slide switch. So I got it mixed up. So this one should be connected. This, not the other way around. So I need my slide switch again. Where did I put it? Hello. Did I turn off my slide switch? Oh, I can't find my slide switch. Oh, it's right here. Okay, so let me put this here. Then where's my spare? Alright, this one is connected to the. Is this a third pin? One more resistor, I believe. Yep. Okay, and then last one to the for the power of our switch at 3.3 volt. But I think I still need to connect this remaining. I hope I have enough cables. Really hope I do. How many are left? So 5 more. It's 1. Let me check. 2. I think these are not gonna be enough for now. I hope I have some. No, it's not. 4. Okay, we have enough. Whew. Okay, so this is connected to the A4. Is that it? Yes, it's the same. This one. I don't think anybody could see what I'm doing, but this one's connected to the third. Let me just put it here. This is oops, last one. I really hope this works. Last one. Okay, moment of truth. Okay, so let me. This is problem number 5. Oh, I haven't declared my board. This one. 2, 4, 6, 8, 2. Okay, so slide. As you can see, the numbers are working on uneven order. So if it's okay, wait. Just let it run again. See, this one runs on odd numbers: 3, 5, 7, 9. So there you go. Our problem number 5 is working properly.
Welcome to the final part of this lab exercise, Program 6. Here, we need our 7-segment display to have a marquee effect. For that, we need 2 7-segment displays or a dual display. This program, as I said, will display a marquee effect of 2 messages based on 2 pieces of light-dependent resistors. In this scenario, if LDR1 or light-dependent resistor 1 is enabled, the 7-segment should show the message hello from left to right. Otherwise, if LDR2 is enabled, the message should display bye from right to left. Let's head on over to our Arduino IDE to begin. First, let's define our pins. LDR1 is equals to A0, LDR2 is equals to A1. Our first 7-segment pins is equals to 2, 3, 4, 6, 7, and 8. Then our second 7-segment pins, 9, 10, 11, 12, 13, A2, and A3. Next, let's define the patterns for hello and bye. Again, this is using a common anode. These are the byte patterns for H, E, L, and O. While these are the byte patterns for B, Y, and E. Let's also declare a byte blank pattern by using all zeros. Now, let's create a function for displaying a single character on a 7-segment display. Let's call it display character with 2 parameters: pins, or the array of integers representing the pins connected to each segment of the 7-segment display, and pattern, which is the array of bytes representing the pattern of the segments to be turned on or off to display the desired character. Now, the for loop. This iterates through each segment of the 7-segment display. Since it has 7 segments, let's start from 0 to I is less than 7 or 6. The next line is basically the same as in the previous program where we set the state of each segment based on their value in the pattern array we declared earlier. We'll also use inverted logic for common anode and a ternary operator. Example, if pattern I is 1, indicating that the segment should be on, low is selected, turning the segment on, since low turns on a segment in a common anode. Likewise, when pattern I is not 1, it turns the segment off even when high is selected. Let's proceed to a new function for displaying hello. First, we'll initiate this variable that stores the number of characters in hello, which is 5 for HELLO. Next, let's define message characters in the order they should appear on the display. Each element of message points to the byte array representing the pattern for a specific character. Let's also write some lines to clear the displays. Let's now write a loop to display each character of the message. If it's the first iteration of the loop, the leftmost display or seg1 pins show the first character. Else, let's first move the character from left to right display, which is seg2 pins and message I-1. Then perform the line above. Don't forget to add a delay. After a full message, the second display will show the last character, while the first display will show a blank pattern because the message has finally moved from left to right. Moving on to the next feature of our program, displaying by on the marquee, this time from right to left. Let's do the same thing from display hello. Our num cars should be 3 now, and we will use the byte array from the by pattern. Unlike in the first one, where we use descending order, here we will employ ascending order because the marquee moves from right to left. Now, we enter a loop once again to display each character of the message. Let's write a condition that checks if the current iteration is within the bounds of the character in the message. If true, it displays the character on the second display. Else, if it's out of bounds, we'll display a blank space. Let's write a condition that checks if the current iteration is greater than 0, meaning it's not the first character being displayed. If true, it displays the previous character on the left display. As you may further visualize it now, it's moving from right to left indeed. Else, if it's the first iteration, segment 1 will display a blank pattern. And of course, don't forget to add a delay. For this part, let's write the setup function. First, we'll initialize pin modes of segment 1 and 2 using a for loop like we did in the previous program. Let's also initialize our light-dependent resistors 1 and 2 and write serial begin. We're now at the main loop function. Hooray! First of all, let's write lines to read the analog values from the two light-dependent resistors or LDR sensors connected to the analog pins. Let's include a print command so we can see the values of the sensors in our serial monitor for debugging purposes. Next, let's add a variable that defines the threshold value that determines whether an LDR is considered activated based on the analog reading. Keep in mind, this will depend on the light conditions of the room wherein the demo is being conducted. In our case, let's make it 600. Finally, let's add conditions to determine display behavior. First, if neither LDR is triggered, both readings are below the threshold. It clears both displays by calling display character with blank pattern. Next, if only LDR1 is activated, the 7 segment will display hello by calling display hello function. Next, if only LDR2 is active, the 7 segment will display by calling display by function. Lastly, in the event of special conditions, let's display both segments as blank patterns. Most importantly, don't forget the delay once again. And that's all for today. It was a lengthy one, this program, but I'm sure it will be worth it once we see the demo video of this one. Keep watching to find out.
Okay, so circuit problem number 6. As you can see, I have already dismantled my problem number 5 circuit because it's just too much for me to see. And now what we have here are 2 7-segment displays. So to start it, let me just put the resistors needed. So this is here. And this one is here. One more. This. And for the first. There you go. And then below the 7-segment display, and this here, and then one here, one more. Okay, so time to connect our 7-segment. So we put this is connected to the 9th. So is this, and then 13th is 4. Oops, I have to connect the 2 so that it's not going here. Yep. To continue. Okay, so this one is connected to A2. A2. And then this one, it's connected to okay. So A3, then here, and then put one in the middle. Okay, so one more. So you can see we have power now. Our photoresistor. Okay, so my camera logged there. So I have my photoresistor here, my light dependent resistor. So I need to let me put one here and then on this side. Oops, got cooked. So try again. Okay, so that's that. We need to put the resistors. One more. Ten more, of course. So let's connect this to this. Oh, my bad. This is positive. And one more to connect the other one to here. Then let us connect this one to A0. One more for okay, I think that's that. Okay, let me try and upload. Oh, I haven't cleared my board. So this is Uno, as usual. Let me upload. What's this? Me. I want it working. Let me try and change. Should it work like this? Okay, so going back to my rev, I think I may have seen what the problem was, so let me. I think it's working now. It is displaying a hello on the 7th segment. Yep. It is working. Try and put this. Okay. Oh, it says bye when you short the. Okay, so that concludes my demonstration for now. I'll see you all next time.